This video lecture is on constant velocity motion. I'm Mrs. Estock. Let's get started. Picture the following scenario. Imagine you're standing at the side of the road, and as you stand there, you observe a car drive by. As that car drives by, how can you tell if it's moving at a constant velocity or if it's accelerating? It really depends on two key pieces of information: the car's displacement and time. If every second of the car's motion it travels the same displacement, in other words, it goes the same distance and in the same direction, then we can say that it's moving at a constant velocity. Let's say that the car is moving at a constant velocity of 20 meters per second to the right. 20 meters per second is about equal to 40 miles per hour, so that every second of this car's motion is traveling at the same velocity. Every second it covers the same distance, and every second, if we were to look at the speedometer, it's the same number, and it's always pointing in the same direction. We could calculate that average velocity by taking displacement divided by time. If the car moves 20 meters east every second, then it's moving with an average velocity of 20 meters per second east. This equation, V equals d over t, is located on the back page of your reference table. And you'll notice that the V has a bar over it, or a line over it. That stands for average. So in this case, we are calculating the average velocity. So on average, the car is traveling at a velocity of 20 meters per second east. If we look at the overall motion of the car for, let's say, 4 seconds of total motion, we can see that every second of its motion, it gains another 20 meters of displacement east. So every second, you add on an additional 20 meters of displacement. And every second, it covers the same displacement, 20 meters east, 20 meters east, 20 meters east. And if you add all of that up, every second you add 20 meters of displacement to your total. So if we start at 0 seconds with a displacement of 0 meters, by 1 second, the total displacement is 20 meters. By 2 seconds, 40 meters. 3 seconds, 60 meters. And at the end, 4 seconds, the total displacement is 80 meters. Now, we can take all of these values and organize them into a data table. Let's make one column for time and one for displacement. And we can see that as time increases by 1 second, the displacement increases by 20 meters. So we can organize all of this into a data table and then graphically represent it with a graph. This is what we call a displacement versus time graph. And we can tell from this graph that we are looking at constant motion because the graph is linear. In other words, it's a straight line. This linear graph has a constant slope. That's why it's a straight line. Remember, the slope of something represents the steepness of the line, and the steepness of this line is the same everywhere. So that means that we have a constant slope. Any motion that is a constant velocity will have a d versus t graph that looks exactly like this, that has a constant slope, in other words. So the shape would be the same. The numbers could be different, but all constant motion has a linear d versus t graph. Now let's say that I asked you to calculate the slope of this line. Well, we know the slope equation from math class. Slope is equal to change in y over change in x. On your d versus t graph, pick 2 points that fall on the line. You can pick any 2 points on this graph because we're looking at a linear graph. So if the slope is constant, it doesn't really matter what 2 points you pick. Here I picked 2 points, one point being that the displacement is equal to 20 meters at 1 second. And the second point that I chose is that the car is displaced 60 meters after 3 seconds of motion. I can use these 2 points to calculate my slope by taking the 2 y values and subtracting them, and divide that by the 2 x values subtracted from each other. Now this gives me an overall slope of 20, but 20 what? Well, that's why it's important to plug in your units as well. The units for the y values are meters because displacement is on the y-axis, and the units for the x-axis are seconds because time is on the x-axis. And if we take a value of meters divided by a value of seconds, we get meters per second. Well, where have we seen this value before? 20 meters per second. Well, hey, that value is equal to the velocity. So we've just discovered that the slope of a displacement versus time graph is equal to velocity. How about that? Now there's another way we can organize motion information and graph it, and that's with a velocity versus time graph. So if we organize our information for time and velocity into a data table, it would look something like this. We still have time starting at 0 seconds and increasing by 1 second each interval until we get to 4 seconds. And the velocity, remember, is constant. We're looking at constant velocity motion. So the velocity stays at 20 meters per second for the entire motion of the car. If we were to graph this in a velocity versus time graph with velocity on the y-axis and time on the x-axis, we still have a linear graph, but this time we notice that the slope, while it is constant, is equal to 0. This will be true for any object that is undergoing a constant motion. The slope of the v versus t graph will be 0. Again, if we think of the slope as the steepness of the line, there is no steepness to this line. It's a flat line, so that means its slope is 0, and its slope is 0 everywhere. We can calculate that slope using the same equation as before. By picking 2 points on our graph, again, we're looking at a linear graph, so you can pick any 2 points. It doesn't matter which 2 you pick. I chose that the car is moving at 20 meters per second at 1 second, and it's also moving at 20 meters per second at 3 seconds. I can take those 2 points and take the y values, 20 meters per second, and subtract them from each other. 20 minus 20 gives me 0, and 0 divided by anything is 0. So for this slope, we get an answer of 0. But what are the units? If we take meters per second divided by seconds, we get meters per second per second. The seconds do not cancel out here, so this is actually equivalent to 0 meters per second squared, which are the units for acceleration. So what we've found here is that the slope of a velocity versus time graph is equal to acceleration. So this means that the car has an acceleration of 0. Well, what does it mean to not be accelerating? That means that over time your velocity is not changing. So what is acceleration? Acceleration is kind of a tricky concept to wrap your head around because it's the rate of a rate. It's the rate of change of your velocity. Velocity itself is the rate of change of your displacement over time. Your acceleration is not simply how much your velocity changes, it's how quickly your velocity changes. It's change in velocity over time. So an example might be if you hit the gas pedal on your car to accelerate. A slow acceleration would be a gradual increase in the pressure that you're applying to that gas pedal, where a quick acceleration or a large acceleration would be slamming your foot on the gas pedal and accelerating at a high rate by having a big change in velocity in a short period of time. There's one more thing that we can calculate from our v versus t graph, and that's the area under the curve. So let's see what this is going to equal. If I calculate the area underneath the line on my velocity versus time graph, I'm looking at the space between the line and the x and y axes. And it turns out the shape that's created is a rectangle, where the height is equal to your velocity and the base is equal to time. Well, I know the equation for a rectangle's area. It's also located on your reference table. It's area equals base times height. So if we take our values for the height and base of this rectangle, the height is equal to 20 meters per second and the base is equal to 4 seconds. If I take 20 meters per second times 4 seconds, the seconds cancel out and I'm left with 80 meters. Where have we seen this value before in this video? Why, that's the value for our total displacement. We've just discovered what the area under a velocity versus time graph represents. If you calculate the area under a v versus t graph, you will get displacement. For constant velocity motion, the shape will be a rectangle. So here you can use the equation area equals base times height. Well, that makes sense. We kind of already did this, didn't we? You can also do this calculation using the equation that we started with, v equals d over t. If you rearrange the equation to solve for displacement, we get displacement is equal to velocity times time. And if we take the velocity of the car, 20 meters per second, multiplied by the total time that it's traveling, we get a total displacement of 80 meters. So either way you look at it, the math ends up being the same. So there are two different ways here to calculate your displacement. So in conclusion, there are three ways that you can have constant velocity motion, whether you're at rest, whether you're moving at a constant velocity at a slow speed, or maybe you're moving at a fast constant velocity. Either of those things, so any of those three options, you'll see the same key facts that we went over today. You'll see that the displacement each second is the same. You'll see that the shape of the displacement versus time graph is linear. You'll see that the shape of the velocity versus time graph gives you a slope of 0, indicating that the object is not accelerating. So that is it for constant motion.